In this lesson, we will derive the Bernoulli equation from the conservation of energy equation for control volumes. Here we have the conservation of energy equation for a control volume with one inlet and one outlet when the flow is steady and one-dimensional. The equation states that the total head at the outlet is equal to the total head at the inlet minus the head loss plus the pump head minus the turbine head. This means that the total head is affected by viscous effects, pumps, and turbines. The viscous effects included in the head loss term are friction due to straight pipes, as well as friction induced by fittings such as valves, elbows, and nozzles. If we have a situation in which the viscous effects are small, the head loss term would be negligible. This would occur if the distance between the inlet and outlet is short, and there are no fittings, or the fittings do not disturb the flow sufficiently to cause flow separation. Flow separation is a condition in which the flow detaches from the wall and eddies are formed, resulting in relatively large losses of mechanical energy. Additionally, if there are no pumps or turbines in the control volume, the pump head and turbine head are zero. Under these conditions, the conservation of energy equation tells us that the total head at the inlet and outlet are approximately the same. If the density does not change significantly from the inlet to the outlet, the specific weight at the outlet equals the specific weight at the inlet. Furthermore, if we make the control volume so narrow that it becomes an infinitely thin streamline, we can drop the average subscript on the velocity since the inlet and outlet now consist of a single point. The conservation of energy equation has now become the pressure at the end of the streamline over gamma, plus the speed at the end of the streamline squared over 2g, plus the elevation at the end of the streamline, equals the pressure at the beginning of the streamline over gamma, plus the speed at the beginning of the streamline squared over 2g, plus the elevation at the beginning of the streamline. We can multiply the equation by the specific weight gamma to give us an equation where each term has units of pressure. The sum of P plus rho v squared over 2 plus gamma z at the end of the streamline is equal to the sum of these three terms at the beginning of the streamline. In fact, the sum of those three terms at any point along the entire streamline is constant. We will denote this constant by the letter C, and we have arrived at the Bernoulli equation. It is important to remember the conditions that must be met in order to use the Bernoulli equation. The flow must be steady, inviscid, which means viscous effects are negligible, incompressible, which means the density does not change significantly, and can only be applied along a streamline. Additionally, the streamline cannot pass through a pump or turbine. One application of the Bernoulli equation is the determination of flow speed. Here we have a pipe with a static pressure tap above point 1 and an L-shaped tube called a pitot tube at point 2. The pipe contains a liquid that is flowing steadily from left to right, and a streamline connects points 1 and 2. The liquid level rises in the pressure tap to a height equal to the pressure head plus elevation head. So we can measure the pressure at point 1 simply by measuring the height of the liquid in the pressure tap. Notice that the liquid level is higher in the pitot tube. As the liquid particle travels from point 1 to point 2, it will decelerate until its velocity becomes 0 at point 2. The particle comes to rest at point 2 because the fluid inside the pitot tube is static. If the distance between points 1 and 2 is not very large, we can assume that viscous effects are negligible and apply the Bernoulli equation. The elevation at points 1 and 2 is the same, so the gamma z terms cancel out on both sides. The speed at point 2 is 0, so the rho v2 squared over 2 term is 0. And we are left with P2 equals P1 plus rho v1 squared over 2. P1 is sometimes called the static pressure, and P2 is called the stagnation pressure because it is the pressure obtained when a fluid particle is decelerated to 0 velocity. Rho v1 squared over 2 is the dynamic pressure because it is related to the motion of the fluid. If we solve the equation for v1, we can determine the velocity of the flow by measuring the difference between the stagnation pressure and static pressure. A pedostatic tube is an L-shaped device that can measure this pressure difference and is often found on the side of aircraft, such as the helicopters shown here. The difference in pressure is then used to determine the aircraft's speed.